Hey mathletes, this is solving exponential and logarithmic equations part 2. We're really going to focus on solving equations where we see logarithms and they have a variable in their argument. Okay, so this property here that we're looking at is the property of logarithms, and the big thing you want to key in at is that if we have the logarithm of both sides, okay, and they have the same base, okay, we can think of this as raising this 2 to the second power and 2 to the second power. And notice that if we raise the logarithm being the exponent, if we raise that and these bases are the same as they are here, they drop away and we're just left with x equals 7. Okay, and so this kind of goes both directions, so we can go that way as well. So we're going to utilize that today as we're solving logarithmic expressions. All right, so the first one we're going to look at is log base 3 of x is equal to 4. Okay, so remember that if we use the definition of logarithms, this is equal to 3 to the 4th equals x. Well, that's easy enough, just to say 3 to the 4th is 81 is equal to x. Okay, but as we get into these more complex logarithmic equations, it's going to be useful to utilize this property. That if we see that base there, if we go ahead and just raise that side to the b, okay, we can raise each side to the b, property of equality, and they're going to be the same. So as we think about solving this with more complex things, the strategy we're going to want to use will be helpful to use is say, all right, I recognize that this is base 3, so I'm going to make this 3 to that, and then 3 to the 4th. Okay, well, these will cancel out, and I just have x left, 3 to the 4th. Okay, which notice you get the same solution here. So new way of kind of thinking about logarithms, but it's going to be useful when solving them. Okay, so here, so I notice I have a base 2, so I'm going to raise this 2 to the power and 2 to this power. Okay, those will cancel out, and I'm left with x minus 6, and 2 to the 5th is 32. Okay, if I add 6 to both sides, I'm going to get x is equal to 38. Okay, and our next example here, similar. I'm going to raise this base 2, so I'm going to raise it to the second power, raise this to the second power. The log and the 2 powers, and I'm just left with the argument, cancel out, so we're at left 5x minus 17 equals 2 to the 3rd is 8. Adding 17 on both sides will give me 5x equals 25. Dividing 5 on both sides, and I get x is equal to 5. Okay. As we're checking answers, we got to remember that if we talk about log, it doesn't matter the base, that this value x, okay, that x, the domain of this, has to be greater than or has to be greater than 0. That when we looked at the function in this graph of x, okay, the logarithm, remember that that graph had a rough shape like this. Okay, it never lived in the quadrants over here. Okay, because when we take a power to something, we're never going to get it to be negative. So we want to make sure that our solutions exist such that when we plug them back in, we don't get a negative value. So I can see if I plug in that 5 value, I get log base 2 of 25 minus 17 is equal to 3. If I simplify that down, I get log of 2 of 8 equals 3, which makes sense because by my definition, 2 to the 3rd is equal to 8. That will be important as we start talking about extraneous solutions. So we need to make sure that the answers that we get for x here, okay, we'll make sure that the argument within here needs to stay positive. Okay. So if we're solving these and we notice we have two logarithms, then we got to use our properties of logarithms to combine them first. Okay, so we know that log of A plus log of B, if we write it as one single logarithm, that becomes multiplication, A times B. So utilizing that over here, okay, I'm going to get, writing this as one logarithm, I get log of 2x times x minus 5 equals 2. Okay. So then, remember, it's not written, so it's assumed that this is base 10. So I'm going to do 10 to this power, 10 to this side. Okay. That'll cancel out the logarithm on the left side, and I'm just left with the argument. I'm going to distribute that 2x to both terms, so I'm going to get 2x squared minus 10x. Well, 10 squared is 100. Well, at this point, I should recognize I have an x and I have an x squared term, so we have a quadratic. Okay, so utilizing our strategies of quadratics, we want to first set it equal to 0. So I'm going to come over here and do that. So I get 2x squared minus 10x minus 100 equals 0. Take a greatest common factor out there before I maybe try and factor this. So 2 comes out. Left with x squared minus 5x minus 50. Okay. In factoring that out, I need things that multiply to negative 50 and add to negative 5. So what works out pretty nice is negative 10 and 5. So my factors end up being x minus 10 and x plus 5 equals 0. So what makes those 0? I get solutions of x equals 10 and negative 5. But I got to check for extraneous solutions. So if I take these values and plug them back into my original equation. So if I plug it back in as 10, I'm going to get log of 20 plus log of 5 equals 2. Okay, so that's all right because notice I don't have negative numbers here. So this is a solution. Okay, but if I plug in negative 5, okay, I'm going to get log of negative 10. And that's a problem. You can type it in your calculator, you'll see a non-real answer. Very similar to if we tried to take a square root of a negative value. We don't come up with imaginary solutions here per se, but we call these extraneous. So it's not really a solution, but it came up typically when we're solving quadratics. So that's extraneous. So our only solution is x equals 10. Okay? Carrying this over, try another example here. So notice I have addition, and I want to write this as a single logarithm first. So I get log base 4, and addition goes to multiplication. So I have x plus 12 times x, okay, equals 3. I'm going to raise both sides to the 4th power, recognizing the base of my logarithm is 4. Okay, that'll cancel out the logarithm on the left, so I'm just left with x times x plus 12 equals 4 to the 3rd, which is 64. Okay. Notice that I distribute on my left side. I get x squared plus 12x equals 64. And with the next term, an x squared term, I have a quadratic. So I'm going to set it equal to 0 and solve that. So I get x squared plus 12x minus 64 equals 0. So I need values that multiply to be negative 64 and 12 if I want to try it by factoring. Nope, you can solve by using your quadratic formula if you'd like, but I prefer factoring if it works. Okay. So as I get this, I see that 16 and a negative 4. Add to 12 and multiply to negative 64, so that ends up being my factors. Okay, my solutions are x equals negative 16 and 4. Okay, checking for extraneous solutions, I can see that when I plug in negative 16, I'm going to get log of 4 of negative 16 plus 12, which is negative, so this is extraneous. And when I plug in 4, I'm going to get log of 4. Well, 4 plus 12 is 16. Log of 4 to the 4th. And that equals 3. Well, here, log 4 of 16, 4 to what power is 16? Well, that's 2. 4 to what power is 4? Well, that's 1. Is 4. 2 plus 1 equal to 3? Sure. Enough. Check. Okay. So we need to remember that this can be applied to our natural base, ln logarithms. Just remember that our base is e. So if there is an e here, if it was a logarithm, right, we're just going to raise this side to the e power, raise this side to the e power. That'll cancel that out, and I have x equals e to the 0.1. Using my calculator, I can type that in, and I get that x is approximately equal to 1.105. Okay. On the next one, okay, similar idea, ln, raise this to the e power, do it to both sides. Property of equality. Those will cancel out. I'm left with the quotient x plus 2 over 3 and e squared. Because e squared is irrational, I'm just going to leave that in its variable form and just isolate x. Okay, it's good practice with our algebra. So I want to undo, so I want to get x by itself, so I want to undo the plus 3 and dividing by 3. So the dividing by 3 will be dealt with first. I'm going to multiply both sides by 3. So I get x plus 2 equals 3e squared minus 2 minus 2. And I get x equals 3e squared minus 2 as the exact answer. And if I type that into my calculator and get an approximate answer there, I'm going to get 20.167. Okay. Next example here, notice that we have a power here. So we want to use our power property. Remember that whether it's a log or an ln of x squared is equal to, where the power can drop down in front, 2 times ln of x. So when I see that, it's going to be much easier to apply that here. So I'm going to get 2 ln of 3x plus 5 equals 4. Since that's multiplication, I can divide this side by 2, divide this side by 2, and I get ln of 3x plus 5 equals 2, because 4 divided by 2 is 2. Now that I've isolated that natural logarithm, I can raise this to the e power, raise this to the e power. Okay? And so I have 3x plus 5 equals e squared. Again, e squared is going to be irrational, so I'm just going to leave it as a variable and isolate my x term. So first thing I'm going to do is subtract 5 from both sides. So I get 3x equals e squared minus 5. Divide both sides by 3. Divide both sides by 3. So I get x equals e squared minus 5 over 3 as an exact solution. And as an approximate solution, we are going to get 0.796. Okay. So notice on our last examples here that we have logs or natural ln's on both sides. Well, don't be thrown off. It's fairly straightforward. If we have these isolated here, well, if we just do e to this side and e to this side, they both just kind of cancel out. So I'm just left with 7x minus 4 equals 2x plus 11. So a very nice Algebra 1 problem that we can solve. You get all my x's on both sides, so I subtract 2x from both sides, and I get 5x minus 4 equals 11. Add 4 to both sides, and I get 5x equals 15. Divide 5 by both sides, and I get x equals 3. Okay. By inspection, I just double check to make sure I'm not going to get a negative value when I plug them in. So I'm going to get ln of 21. 3 times 7 is 21 minus 4 is 17, which equals ln of 3 times 2 is 6, and that's 17. So check, those are going to work. Okay, in our final example here, similar, we're going to raise this to the e power, raise this to the e power. Okay, we get 4x minus 7 equals x plus 5. Okay, subtracting x from both sides, we get 3x minus 7 equals 5. Adding 7 to both sides, I get 3x is equal to 12. And dividing by 3 on both sides, I get x is equal to 4. Okay, that concludes our notes today on solving exponential and log equations part 2. Please bring any questions you might have to office hours.